evening, students. Today I will be going over my chemistry honors video for the chemistry course of the second semester. Let's move on. So the agenda for today is to solve the following problem. Imagine that you have a chamber in which a chemical reaction is taking place. The chamber is surrounded by 1,000 milliliters of water, where 1 milliliter equals 1 gram, of liquid water at room temperature, which is 21 degrees Celsius. If approximately 250 moles of a product is produced in the reaction, what change will be experienced by the water surrounding the reaction chamber? Assume that energy absorbed or released by the reaction is either absorbed from the surrounding water or released to the water. So this question essentially tests the knowledge that we have acquired throughout the whole semester. Let's break it down into each individual part. So the chemical reaction that I was given was as follows. C2H2, or carbon 2 atoms of carbon, 2 atoms of hydrogen in their gas state, plus 2 more hydrogen atoms in their gas state, combines to make the compound product of 2 carbon atoms and 6 hydrogen atoms in their gas state. And this chemical reaction is a synthesis reaction because 2 or more, in our case 2, reactants are coming together to make one single compound complex product. So let's break down the chemicals that are involved in my chemical reaction. As you can see on the left side, we have carbon, and carbon has an atomic number of 6. It also has an average atomic mass of 12.1. If we would subtract the atomic number from the average atomic mass, we would get the number of neutrons in this atom, which would be 6.01. And a neutral atom of carbon, the atomic number would equal the amount of electrons in the atom, which would be 6. So the group number of carbon is 14, the period number is 2, and the family of carbon are the nonmetals, or more specifically, the carbon family. The electron configuration, or how the electrons are put into what orbitals, is as follows. 2s2, 2p2. The hydrogen atoms have an atomic number of 1 and an average atomic mass of 1.01. Now, the average atomic mass is solved by taking all of the isotopes and adding up their atomic mass and dividing it by the number of isotopes taken into consideration, and that's the average atomic mass. The group number of hydrogen is 1, and the period number of hydrogen is 1 as well. The family is the nonmetals, and the electron configuration is 1s1, since there is only one atomic number, so it is put into that orbital. So, the law of conservation of energy states that energy cannot be created nor destroyed, so we have to make sure that our chemical equation is actually balanced before we begin digging in deeper into it. Let's start by making an inventory list and dividing our chemical reaction in half, dividing the reactants on the left side and the products on the right side. Let's make our inventory list. So on the reactant side, or the left side, we have 2 atoms of carbon and 4 atoms of hydrogen. On the right side, with the products, we have 2 atoms of carbon and 6 atoms of hydrogen. So as you can see here, we ended up with more hydrogen atoms than we started, 2 to be exact. So to balance this chemical equation and for it to meet the standards of the law of conservation of energy, we have to add a 2 in front of the H2 right here to have 2 more hydrogen atoms. And when we add that, we can cross out the 4 and change it to 6, since now we have 4 hydrogen atoms plus 2 hydrogen atoms, and that makes 6. And now that matches up with what we ended with. So now let's calculate the enthalpy of reaction. And to do that, we can subtract the reactants from the products. And when I saw the enthalpy of reaction chart, I was able to acquire some values for the reactants and products in our chemical equation. So C2H2 is equal to 227 kilojoules per mole, and H4 is equal to 0 kilojoules per mole, and the product C2H6 is equal to negative 84.5 kilojoules per mole. So now that we have this information, we can solve. So negative 84.5, which is the products, subtracted by 227 kilojoules per mole, the reactants, it's going to give us a total of negative 311.5 kilojoules per mole, which is the change of enthalpy. So now, let's find the energy released if 250 moles of product are given. So you can find that by multiplying the change in enthalpy by 250 moles. And so our change in enthalpy resulted in negative 311.5 kilojoules per mole. And so since the formula is to multiply that times 250, when we do that, we end up with negative 77,875 kilojoules. Because the units of moles end up canceling out when you multiply them. So to convert that into joules, simply joules and not kilojoules, we can multiply negative 77,875 kilojoules times 100 to get simply joules. And when we do that, we get, let's see, negative 77,875,000 joules. As you can see here, they cancel out. So let's now dig into the energy required to change our liquid into gas. So the formula for this is Q equals M times C, change specific heat capacity of liquid, times delta T. And M represents the mass of the liquid. The specific heat capacity stands for the amount of heat required to heat our product. And delta T stands for the change in temperature, which we would subtract the initial minus the final. Let's move on and plug in some numbers. So since we have 1,000 milliliters and 1 milliliter equals 1 gram, that gives us 1,000 grams of water times 4.18 joules over grams degrees Celsius, which is the specific heat capacity of water, times 79 degrees Celsius, which is the amount of heat required to change the liquid to the gas. Since we start off with 21 degrees Celsius, and 21 degrees plus 79 degrees gives us 100 degrees, which is the point at which water turns to gas. So when we multiply the Celsius, the units of Celsius, degrees Celsius, ends up canceling itself, and the units of grams actually ends up canceling out as well. And we are just left with the units of joules, and we end up with 330,220 joules. And that's actually the energy required to change our liquid into gas. Now let's find the latent heat of vaporization. And the formula for the latent heat of vaporization is Q equals M times delta H of vap, where M represents mass, Q represents the heat energy, and the delta H vap represents a specific value. So let's input our numbers. When we plug in our numbers, we get Q equals 1,000 grams times 2,260 joules over grams. And when we solve and multiply, the units of grams end up canceling themselves out, and our total ends up being 2,260,000 joules, since we're only left with the unit of joules. Now let's add up the heat required for the latent heat of vaporization with the heat required to change our water from liquid to a gas. So let's add 2,260,000 joules plus 330,220 joules to get a total of 2,590,220 joules, which is the heat required from changing our water from a liquid to a gas, while that also includes the phase change of the latent heat of vaporization. And so now let's find the energy released. And the energy released can be found by subtracting the 77,875,000 joules, which is the change in enthalpy that we found before, and you subtract 2,590,220, which is the value that we just found in the last slide, which is the heat required to change it from a liquid to a gas, while including the phase change. And when we subtract those, our final answer is going to be 75,284,780 joules. So now let's find the change in temperature. So let's plug in the values that we know, and we'll leave the values that we don't know and make them variables that we don't know of. So let's plug in the energy that we know of, which is 75,284,780 joules, equals 1000 grams, which is the weight, times 1.99 joules over grams degrees Celsius, which is the specific heat capacity for gas since our liquid water is now in the gas state, times delta T, and delta T doesn't have a value since we don't know its value or the numbers or the change in temperature, and that's what we're trying to find out. So it's going to be left plain without a number. So we can start off by dividing both sides by 1.99 joules over grams degrees Celsius. And when we do that, we can cancel out like terms and also units. So we could cancel out joules on both sides, and we're left with 37,831,547.74 grams degrees Celsius equals 1000 grams times delta T. Now, since we want to get the variable alone, let's divide out 1000 grams to both sides. And when we do that, we can cancel out grams on that side, and we can cancel out the units of grams on the left side. Then we're left with delta T is equal to 37,831.55 degrees Celsius. But that's not all. We still need to add the 79 degrees that we added at the beginning. So let's add that. And our final change in temperature is going to be 37,910.55 degrees Celsius. Phase change or no? Definitely. Since we started our process with a liquid at 22 degrees Celsius, which is room temperature, and it went from a phase change, and it went from a liquid to a gas, it went through a heat transfer of energy, and the heat transfer came from the chemicals stored in the chamber, and that chemical was exothermic because it was giving off heat energy, and we know this because of the negative answer that we got in the change in enthalpies. And that doesn't mean that we have negative energy like some voodoo magic energy, but it just means that the chemical was giving off energy, and we ended up with a gas that was at 37,932.55 degrees Celsius, which is at an extreme temperature. So we definitely went through a phase change, and the water was actually endothermic because it gained heat from the chemical stored in the chamber, and it raised its temperature. So thanks for watching my video. I hope that you learned more on these topics like changes in enthalpy, phase changes, etc. Be sure to watch my other videos for guidance on other topics. Thanks.